There is a number that astronomers use to describe the distances between stars. It is not a number in kilometers, because kilometers would require so many digits that the figure would become meaningless to the human mind. It is not a number in miles. It is a number measured in the distance that light itself travels across an entire year of uninterrupted motion through the vacuum of space. That number is called a light year. Tonight, we are going to spend time with that number. We are going to turn it over slowly, examine it from different angles, and try to understand what it actually means for a species like ours, a species that evolved on a small rocky world, that has only recently learned to leave that world at all, and that has never traveled farther from home than the moon. This is Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Get comfortable. There is no rush here. We will move through these ideas gently, allowing each one to settle before moving to the next. By the time we are finished, you will have a sense of just how large one light year truly is, and what it would mean for humanity to attempt to cross even that smallest of cosmic intervals. We will begin with the definition of a light year itself. Then we will trace the history of how humanity came to measure the speed of light. We will look at how light travel time already shapes our relationship with the solar system. And then we will step outward, past the planets, past the edge of our sun's reach, toward the nearest stars. We will examine the spacecraft we have built, the physics that constrain us, and the ideas that scientists and engineers have proposed to push beyond those constraints. And at the end, we will simply sit with the scale of it all and consider what these distances mean for our understanding of where we are. Chapter 1. What is a light year? The word light year sounds like a measurement of time. The word year is right there in it, and so it is easy to assume, on first hearing it, that a light year describes some kind of duration, but it does not. A light year is a measurement of distance. It is the distance that light travels through the vacuum of space over the course of 1 year. Nothing more, nothing less. To understand why astronomers use this unit, rather than something more familiar, it helps to appreciate the problem they face. The distances between objects in the universe are so vast that conventional units simply break down under the weight of all those zeros. The kilometer is a perfectly good unit for measuring the distance between two cities, or even the distance from the Earth to the Moon. The Moon is roughly 384,000 kilometers away. That number is manageable. You can hold it in your mind. But when you try to express interstellar distances in kilometers, the numbers become unworkable. The nearest star to our Sun, a small red dwarf called Proxima Centauri, is approximately 40 trillion kilometers away. 40 trillion. Written out, that number has 13 digits. It is not a number that communicates anything intuitively. It does not help you feel the distance. It only tells you that the distance is very, very large. A light year solves this problem by anchoring the measurement to something that, while still impossibly fast by human standards, at least has a physical meaning. Light is the fastest thing in the universe. When we say that something is 4 light years away, we are saying that even light, traveling at its maximum speed, would take 4 years to get there. That framing gives the distance a kind of emotional weight that a string of zeros cannot provide. So how far is 1 light year in more conventional terms? Light travels at approximately 299,792 kilometers per second. In 1 minute, it covers roughly 17.9 million kilometers. In 1 hour, it covers about 1,079,000,000 kilometers. In 1 day, it covers approximately 25.9 billion kilometers. And in one full year of 365 days, light travels a total distance of about 9.46 trillion kilometers. That is 1 light year, 9.46 trillion kilometers, or, in miles, roughly 5.88 trillion miles. The light year is not the only unit astronomers use for large distances. There is also the astronomical unit, which is the average distance from the Earth to the Sun, approximately 149,600,000 kilometers. Astronomical units are useful for measuring distances within the solar system, and there is the parsec, which equals approximately 3.26 light years, and which is preferred by many professional astronomers for technical calculations. But the light year remains the unit most people encounter, and for good reason. Its connection to the behavior of light makes it the most intuitively meaningful of the three. It is worth pausing for a moment to appreciate just how recent our knowledge of this unit is. For most of human history, people had no idea how far away the stars were. They appeared as points of light in the sky, beautiful and fixed, and their distances were entirely unknown. It was not until the 19th century that astronomers first succeeded in measuring the distance to another star. The first reliable stellar parallax measurement, made in 1838 by the German astronomer Friedrich Bessel, placed the star known as 61 Cygni at a distance of about 10.3 light years. For the first time in history, a human being had determined how far away a star was. The universe suddenly had a measurable depth. Since then, the methods for measuring cosmic distances have grown increasingly sophisticated. Modern astronomy uses a layered system of techniques, sometimes called the cosmic distance ladder, to measure distances ranging from nearby stars all the way to the edges of the observable universe. But the light year remains the standard unit for describing those distances to anyone who wants to understand them without a degree in mathematics. 1 light year, 9.46 trillion kilometers, a number that is simultaneously precise and almost impossible to imagine. That tension between knowing a number exactly and being unable to feel its true scale is something we will return to throughout this video. Chapter 2. The speed of light. Before we can fully appreciate what a light year means, we need to spend some time with the speed of light itself. Because the speed of light is not just a large number. It is one of the most fundamental constants in all of physics, and its value has shaped everything from our understanding of space and time to the structure of the universe itself. Light travels at 299,792 kilometers per second. This figure is so precise and so important that in 1983, the international scientific community redefined the meter itself in terms of the speed of light. The meter is now officially defined as the distance light travels in 1,299,792,458th of a second. In other words, the speed of light is now treated as an exact value, baked into the very definition of distance. But how did we come to know this number? The story of measuring the speed of light is one of the more gradual and fascinating threads in the history of science. For most of human history, there was genuine debate about whether light had a speed at all. Many ancient philosophers, including Aristotle, believed that light traveled instantaneously, that it was simply present everywhere at once the moment a source was ignited. This seemed reasonable given everyday experience. When you light a candle, the room does not fill with light gradually, the way water fills a bowl. It simply becomes bright, all at once, The first serious scientific attempt to measure the speed of light was made by the Italian astronomer Galileo Galilei in the early 17th century. He and an assistant stood on two hilltops some distance apart, each holding a covered lantern. The idea was that Galileo would uncover his lantern, and his assistant would uncover his own lantern the moment he saw Galileo's light. By measuring the delay, Galileo hoped to calculate the speed. The experiment failed. The delay was too small to measure with the tools available, and Galileo concluded only that if light had a finite speed, it was extremely fast. The first successful measurement came from an unexpected direction. In 1676, the Danish astronomer Ole Romer was studying the moons of Jupiter, and in particular the timing of eclipses of the moon Io as it passed behind the planet. He noticed something curious. The eclipses did not occur at perfectly regular intervals. When the Earth was moving away from Jupiter, the eclipses appeared to happen slightly later than expected. When the Earth was moving toward Jupiter, they appeared to happen slightly earlier. Romer correctly interpreted this as evidence that light had a finite speed, and that the variation in timing was caused by the changing distance that light had to travel as the Earth moved in its orbit. His estimate for the speed of light, though not precise by modern standards, was in the right ballpark, and it was the first time anyone had demonstrated that light took time to travel. Over the following 2 centuries, increasingly precise measurements were made by a series of physicists and astronomers. In the 19th century, the French physicist Hippolyte Fizeau used a rotating toothed wheel to measure how long it took light to travel to a mirror 8 kilometers away and return. His result was within about 5% of the accepted modern value. His contemporary Léon Foucault improved the method using a rotating mirror, achieving even greater precision. By the late 19th century, the American physicist Albert Michelson had devoted much of his career to measuring the speed of light with ever-increasing accuracy. Using carefully designed interferometers and rotating mirrors, he achieved measurements that were extraordinarily close to the modern accepted value. Michelson won the Nobel Prize in Physics in 1907, the first American to do so, and his work on the speed of light was a central part of that recognition. What makes the speed of light truly remarkable, beyond its precise numerical value, is what it means for the structure of the universe. In 1865, the Scottish physicist James Clerk Maxwell showed mathematically that light was a form of electromagnetic radiation, and that its speed could be derived from the fundamental properties of electricity and magnetism. This was a profound result. It meant that the speed of light was not arbitrary. It was woven into the fabric of the universe, determined by the same constants that govern all electromagnetic phenomena. And then, in 1905, Albert Einstein took that insight a step further. In his special theory of relativity, Einstein proposed that the speed of light in a vacuum is the same for all observers, regardless of their own motion or the motion of the light source. This is not an obvious statement. If you are standing on a train moving at 100 kilometers per hour and you throw a ball forward at 50 kilometers per hour, an observer standing on the platform will see the ball moving at 150 kilometers per hour. Speeds add. That is our everyday experience. But light does not behave this way. If you are on a spacecraft moving at half the speed of light and you shine a flashlight forward, an outside observer will not see the light moving at 1.5 times the speed of light. They will see it moving at exactly the speed of light, and so will you. This constancy of the speed of light, strange as it seems, has been confirmed by every experiment ever devised to test it. The consequences of this constancy are extraordinary. Time slows down for objects moving at high speeds. Space contracts in the direction of motion. Mass increases as velocity increases. These effects are not just theoretical curiosities. They are real, measurable phenomena that must be accounted for in technologies, ranging from GPS satellites to particle accelerators. We will return to them in more detail when we discuss relativistic travel later in this video. For now, what matters is this. The speed of light is approximately 300,000 kilometers per second. It is the fastest speed at which anything in the universe can travel, and it defines the unit we use to measure the distances between stars. 1 light year is the distance covered at that extraordinary speed over the span of an entire year. Chapter 3. Light travel time in daily life. There is something quietly remarkable about the fact that we already live with the speed of light every day, even if we rarely think about it in those terms. Every time we look at the sky, we are not seeing the universe as it is. We are seeing it as it was. The light reaching our eyes left its source some time ago, and we are receiving it now, after its long journey across space. This is not a metaphor or an approximation. It is a physical fact, and it applies to everything from the nearest streetlight to the most distant galaxy. Let us start close to home. When you look at the moon, the light entering your eyes is not showing you the moon as it exists at this moment. It is showing you the moon as it was approximately 1.28 seconds ago. That is how long it takes light to travel from the lunar surface to the Earth, across a distance of roughly 384,000 kilometers. 1.28 seconds is not a long time. It is short enough that for most practical purposes, we can say we are seeing the moon in real time. But technically, we are not. We are always looking into the past. Move a little farther out, and the delay becomes more noticeable. The Sun is approximately 149.6 million kilometers from Earth. Light takes about 8 minutes and 20 seconds to cross that distance. When you look at the Sun, the image you see left the solar surface 8 minutes and 20 seconds ago. If the Sun were to somehow vanish at this very moment, we would not know for another 8 minutes and 20 seconds. We would continue to see it shining in the sky, feeling its warmth, until that last pulse of light finally arrived and then stopped. This 8-minute delay has a name among astronomers. The distance from the Earth to the Sun is called 1 astronomical unit, and it is often described in terms of light travel time as approximately 8 light minutes. It is a useful reference point for understanding the solar system, because all the other planetary distances can be expressed as multiples of this familiar unit. Mars, for example, varies in its distance from Earth, depending on where both planets are in their orbits. At its closest approach, Mars can be about 3 light minutes away. At its farthest, it is closer to 22 light minutes. This variability has significant practical consequences for space missions. When NASA controllers send a command to a rover on Mars, they cannot have a real-time conversation with it. The signal takes somewhere between 3 and 22 minutes to arrive, and then another 3 to 22 minutes for any response to come back. Every interaction is a slow, patient exchange across a gulf of space that light itself takes many minutes to cross. Jupiter, the largest planet in the solar system, is on average about 43 light minutes from Earth. Saturn is roughly 1 light hour and 20 minutes away. Uranus is closer to 2 light hours and 40 minutes. Neptune, the outermost of the 8 planets, sits at an average distance of about 4 light hours from Earth. These numbers give the solar system a kind of temporal texture. When the Voyager 2 spacecraft made its flyby of Neptune in 1989, the signals it transmitted back to Earth took approximately 4 hours to arrive. The scientists and engineers at the Jet Propulsion Laboratory were not watching events unfold in real time. They were watching history, arriving slowly in the form of radio waves traveling at the speed of light across 4 light hours of space. And then there is the matter of starlight itself. When you step outside on a clear night and look up at the stars, you are not seeing any of them as they currently are. You are seeing a collection of different moments in the past, layered on top of each other in a single field of view. Sirius, the brightest star in the night sky, is about 8.6 light-years away. The light reaching you from Sirius tonight left that star 8.6 years ago. Betelgeuse, the red supergiant in the constellation Orion, is somewhere between 500 and 700 light-years away, meaning the light you see from it tonight left the star during the medieval period on Earth. Some of the stars visible to the naked eye are thousands of light-years away. When you look at them, you are looking thousands of years into the past. And when astronomers study distant galaxies with powerful telescopes, they are looking back millions or even billions of years. The Hubble Space Telescope has captured images of galaxies so distant that the light in those images has been traveling toward us since the universe was less than 1 billion years old. In this sense, every telescope is a time machine. The deeper you look into space, the further back in time you see. The night sky is not a static picture of the present. It is a layered archive of the past, with different depths corresponding to different eras of cosmic history. This relationship between distance and time is one of the things that makes astronomy unique among the sciences. A geologist studying ancient rock formations is looking at the deep past through evidence that has been preserved and transformed over time. But an astronomer looking at a distant galaxy is receiving direct light from that galaxy as it actually existed billions of years ago. The signal has not been transformed. It has simply been traveling at the speed of light for all that time. This is the context in which the light year exists. It is not just a unit of distance. It is also a unit of time delay. When we say that a star is 10 light years away, we are also saying that everything we know about it is 10 years out of date. The universe we observe is always, necessarily, a universe of the past. Chapter 4. Mapping the Solar System. To truly feel the scale of a light year, it helps to first develop a clear sense of the solar system, the space we actually inhabit. Because even our own cosmic neighborhood, tiny by the standards of interstellar space, is already far larger than most people intuitively appreciate. The solar system is typically described as consisting of the Sun at the center, 8 planets in roughly circular orbits, a belt of rocky asteroids between Mars and Jupiter, and beyond Neptune, a region of icy bodies known as the Kuiper Belt. But this description, accurate as far as it goes, tends to understate the sheer emptiness of the space involved. Let us start with a thought experiment. Imagine shrinking the entire solar system to a more human scale. If the Sun were the size of a basketball, roughly 24 centimeters in diameter, then the Earth would be a small ball bearing about 2.6 millimeters in diameter. Located roughly 26 meters away, Mars would be about 40 meters from the basketball Sun. Jupiter, the first of the gas giants, would be a marble-sized sphere some 135 meters away. And Neptune, at the outermost edge of the classical planetary system, would be located roughly 800 meters from the basketball sun. On this scale, the entire planetary solar system, from the Sun out to Neptune, fits within a circle less than 2 kilometers across. That feels manageable. That feels like something you could walk around. But the solar system does not end at Neptune. Beyond Neptune lies the Kuiper Belt, a broad disk of icy objects extending from about 30 astronomical units to roughly 50 astronomical units from the Sun. Pluto lives here, along with many other dwarf planets and smaller bodies. On our basketball scale, the outer edge of the Kuiper Belt would be about 1.3 kilometers from the Sun. And beyond the Kuiper Belt lies something even more distant, the Oort cloud. The Oort cloud is a vast, roughly spherical shell of icy bodies believed to surround the solar system at enormous distances. Its inner edge is thought to begin at roughly 2,000 astronomical units from the Sun, and its outer edge may extend as far as 100,000 astronomical units or more. 100,000 astronomical units. On our basketball scale, that would put the outer edge of the Oort cloud somewhere between 2.5 and 5 kilometers away from the Sun. The entire planetary system, all 8 planets, would fit in a small park at the center. The full extent of the solar system, including the Oort cloud, would stretch for kilometers in every direction. Now, here is the key comparison. 1 light-year is approximately 63,241 astronomical units. The outer edge of the Oort cloud, at perhaps 100,000 astronomical units, actually extends a little beyond 1 light-year from the Sun. In this sense, the solar system itself, if you include the Oort cloud, is roughly 2 light-years in diameter. But the nearest star, Proxima Centauri, is 4.24 light-years away. That means the gap between the edge of our solar system and the nearest neighboring star is approximately 2 to 3 light-years of essentially empty space. On our basketball scale, that gap would be measured in tens of kilometers. The nearest star would be perhaps 50 to 70 kilometers from our basketball sun. Imagine standing next to a basketball sitting in the middle of a field. The nearest other basketball is 50 kilometers away in the next city. Everything in between is, for practical purposes, empty. That is the density of stars in our region of the galaxy. The spacecraft we have actually sent beyond the planets give us a useful reference point for how real this emptiness is. Voyager 1, launched in 1977, and the most distant human-made object ever built, has been traveling for nearly half a century. It moves at approximately 17 kilometers per second relative to the Sun, which is fast by any human standard. At that speed, Voyager 1 is currently somewhere around 23 to 24 billion kilometers from Earth, a distance of roughly 160 astronomical units. That is impressive. That is genuinely far. But expressed in light years, the distance is approximately 0.0025 light years. Voyager 1, after nearly 50 years of continuous travel, has covered less than 1/300th of a light year. The nearest star is 4.24 light years away. At Voyager's current speed, it would take approximately 73,000 years to reach Proxima Centauri, if it were headed in that direction, which it is not. This is the scale of the problem. This is what a light year means in practical terms. Our fastest spacecraft, after a half-century of travel, has barely scratched the surface of the distance we are discussing. 1 light year is not just far. It is a kind of far that our current technology cannot meaningfully address. we will look more carefully at that technology and at what it would actually take to close this gap in the chapters ahead. But first, let us spend a little more time with the solar system itself, because there are a few more landmarks worth noting before we step out beyond its edge. The asteroid belt, located between Mars and Jupiter, at distances of roughly 2 to 3.5 astronomical units from the Sun, is often imagined as a dense field of rock, the kind of navigational hazard depicted in science fiction films. In reality, it is remarkably empty. The total mass of all the objects in the asteroid belt is less than 4% of the mass of the Moon. The average distance between individual asteroids is hundreds of thousands of kilometers. Spacecraft passing through the belt face almost no risk of collision. The emptiness we see at the planetary scale continues right down to the smaller structures within it. Jupiter itself deserves a moment of attention, not just as the largest planet in the solar system, but as a gravitational force that has shaped the architecture of everything around it. Jupiter's immense gravity has influenced the orbits of asteroids, captured numerous moons, and may have played a role in protecting the inner planets from some fraction of cometary impacts over geological time. It sits at 5.2 astronomical units from the Sun, and its light travel time from Earth varies between roughly 33 and 52 minutes, depending on orbital positions. Saturn, with its extraordinary ring system, lies at 9.5 astronomical units. The rings themselves, despite being up to 300,000 kilometers in diameter, are extraordinarily thin, in some places only 10 meters thick. Saturn's light travel time from Earth is typically between 68 and 90 minutes. Uranus and Neptune, the two ice giants, are so distant that they were unknown to ancient astronomers. Uranus was first observed telescopically by William Herschel in 1781. Neptune's existence was predicted mathematically before it was ever observed, based on irregularities in Uranus's orbit, and it was confirmed by telescope in 1846. Neptune's average light travel time from Earth is about 4 hours and 10 minutes. Beyond Neptune, the Kuiper Belt objects include not just Pluto, but a growing list of dwarf planets, many of them discovered in the 21st century. Objects like Eris, Makemake, and Haumea orbit in this distant region at distances of 30 to 100 astronomical units. Some Kuiper Belt objects have orbits so elongated that they spend most of their time well beyond 100 astronomical units from the Sun. And then there is Sedna, a mysterious object first discovered in 2003, with an orbit so elongated that it ranges between roughly 76 and 937 astronomical units from the Sun. Sedna's orbital period is estimated at around 11,000 years. It is one of several objects thought to possibly be influenced by the gravity of a hypothetical undiscovered large planet in the outer solar system, an object astronomers have sometimes called Planet 9. All of this from Mercury at 0.39 astronomical units to the hypothetical outer Oort cloud at 100,000 astronomical units constitutes our solar system. It is, as we noted, roughly 2 light-years in diameter at its maximum extent, and yet even this enormous structure is dwarfed by the gap between us and the nearest star. That gap, that vast emptiness between solar systems, is where a light-year truly comes into its own as a unit of measurement, and it is toward that emptiness that we now turn. Chapter 5. The Edge of the Solar System. We have already met Voyager 1 in the previous chapter, but it deserves a more careful examination here, because it is our most direct and honest answer to the question of how far humanity has actually traveled. Not in theory, not in simulation, not in the mathematics of proposed future missions, but in physical reality, with actual hardware that we built and launched and tracked across decades of time. Voyager 1 was launched on September the 5th, 1977. It was not designed to leave the solar system. Its primary mission was to study Jupiter and Saturn, which it did with extraordinary success, returning detailed images and scientific data from both giant planets and their moons. But after completing those flybys, Voyager 1 was on a trajectory that would carry it out of the planetary system entirely, and NASA decided to let it keep going. The spacecraft is small by any measure. It weighs about 825 kilograms, roughly the mass of a small car. It carries a suite of scientific instruments, a radio antenna 3.7 meters in diameter, and a power source consisting of 3 radioisotope thermoelectric generators, which convert the heat from decaying plutonium into electricity. That power source has been slowly weakening for nearly 5 decades, and NASA has had to gradually shut down instruments to conserve energy. But the spacecraft is still transmitting. It is still out there, still sending signals back across an almost incomprehensible distance. As of the mid-2020s, Voyager 1 is traveling at approximately 17 kilometers per second relative to the Sun. That is roughly 61,000 kilometers per hour. By any earthly standard, that is extraordinarily fast. A commercial aircraft travels at about 900 kilometers per hour. A high-speed rifle bullet travels at about 1,000 meters per second, or 3,600 kilometers per hour. Voyager 1 is moving at nearly 17 times the speed of a bullet, and yet, expressed as a fraction of the speed of light, Voyager 1's velocity is about 0.0057%. It is moving at roughly 1/17,000th of the speed of light. The speed of light is not just fast. It is in a completely different category of fast, so far beyond our engineering achievements that simple comparisons barely capture the gap. In 2013, after 36 years of travel, Voyager 1 crossed what scientists believe to be the heliopause, the boundary where the solar wind, the constant stream of charged particles flowing outward from the Sun, finally weakens to the point where it can no longer push back against the interstellar medium. This boundary is considered by many scientists to mark the functional edge of the solar system, the point at which the Sun's direct physical influence gives way to the broader environment of interstellar space. Voyager 1 became the first human-made object to enter interstellar space. The heliopause is located at roughly 120 to 123 astronomical units from the Sun, depending on where you measure it. In light travel time, that is about 16 to 17 light hours. Not light years, light hours. Voyager 1, after 36 years of travel, had crossed a boundary that light itself crosses in about 17 hours. Voyager 2, Voyager 1's sister spacecraft, launched about 2 weeks earlier in August of 1977, but on a different trajectory, crossed the heliopause in 2018, at a distance of about 119 astronomical units. Scientists were able to compare the data from both crossings, getting their first direct measurements of conditions in the interstellar medium from 2 different locations simultaneously. Beyond the heliopause lies a region called the heliosheath's outer boundary, and beyond that, eventually, the hypothetical Oort cloud. As we noted in the previous chapter, the Oort cloud may extend as far as 100,000 astronomical units from the Sun, and its outer edge may reach slightly beyond 1 light-year. Voyager 1 will not reach the inner edge of the Oort cloud for another 300 years or so. It will not fully exit the Oort cloud for perhaps 30,000 years. 30,000 years. That is longer than recorded human history. It is longer than the time since the last ice age. And Voyager 1, moving at 17 kilometers per second, will spend all of that time simply crossing the outermost, most diffuse reaches of our own solar system before it can truly be said to have left. The other spacecraft we have sent to the outer solar system tell a similar story. Pioneer 10 and 11, launched in 1972 and 1973 respectively, were the first spacecraft to travel through the asteroid belt and make direct observations of Jupiter. They are also on trajectories that will carry them out of the solar system, though we lost contact with Pioneer 10 in 2003 and with Pioneer 11 in 1995. New Horizons, launched in 2006 and famous for its spectacular flyby of Pluto in 2015, is also heading outward. It is currently moving at about 14 kilometers per second, somewhat slower than Voyager 1. None of these spacecraft were designed with interstellar travel in mind. They are ambassadors of a sort, carrying golden records or plaques with information about humanity, sent not because anyone expects them to be found anytime soon, but because the universe is large and time is long, and it seemed like a worthy gesture. Voyager 1's golden record, which contains sounds and images of Earth, will drift through interstellar space for billions of years after every human being who contributed to it has died. It may never be found, but it will keep going. The edge of the solar system, then, is not a sharp line. It is a gradual fading of the sun's influence across an enormous range of distances. The heliopause is one definition of the edge, at roughly 120 astronomical units. The outer Oort cloud is another, at perhaps 100,000 astronomical units. Neither of these is the edge of the distance we are trying to cross. 1 light-year is 63,000 astronomical units. The nearest star is 4.24 light-years away. We are talking about distances that make the entire extent of Voyager 1's journey, after nearly 50 years, look like the first step of a very long walk. Chapter 6. The Nearest Stars. Step outside the solar system, past the heliopause, past the hypothetical reaches of the Oort cloud, and you enter the interstellar medium. This is the space between the stars, and it is, by almost any definition, empty. Not perfectly empty. There are trace amounts of gas, mostly hydrogen and helium, along with dust particles, cosmic rays, and magnetic fields threading through the void. But the density of matter here is extraordinarily low, on the order of 1 atom per cubic centimeter on average. For comparison, the air you are breathing right now contains approximately 27 million trillion molecules per cubic centimeter. The nearest star to our Sun is Proxima Centauri, a red dwarf located approximately 4.24 light-years away. It is part of a triple star system known as Alpha Centauri, which also includes 2 Sun-like stars, Alpha Centauri A and Alpha Centauri B, orbiting each other at a distance of roughly 23 astronomical units. Proxima Centauri orbits this pair at a much greater distance, somewhere around 13,000 astronomical units, and may take as long as 500,000 years to complete one orbit around its companions. Proxima Centauri is a small, dim star, only about 1/8 the mass of the Sun, and roughly 1/7 its diameter. It is so faint that despite being our nearest stellar neighbor, It cannot be seen with the naked eye from Earth. It was not discovered until 1915, when the Scottish astronomer Robert Innes identified it using a telescope at the Union Observatory in Johannesburg. Despite its modest size, Proxima Centauri is of great interest to astronomers for one particular reason. In 2016, researchers announced the discovery of a planet orbiting Proxima Centauri within its habitable zone. The range of distances from a star where liquid water could potentially exist on a planetary surface. This planet, known as Proxima Centauri b, has a minimum mass roughly similar to Earth's and orbits its star every 11.2 days. Whether it is truly habitable is unknown. Red dwarf stars like Proxima Centauri are known for intense stellar flares that could strip away planetary atmospheres, and the planet is thought to be tidally locked, meaning one side always faces the star while the other remains in permanent darkness. But the existence of a roughly Earth-sized world at our nearest stellar neighbor has given the idea of interstellar travel a concrete and meaningful destination. In 2019, a second planet candidate was identified in the Proxima Centauri system, designated Proxima Centauri c, orbiting much farther from the star and likely too cold to be habitable. And in 2022, evidence emerged for a possible third planet, though its status remains under investigation. Alpha Centauri A and B, the two Sun-like stars in the system, are located 4.37 light-years from Earth, slightly farther than Proxima. They orbit each other with a period of about 79.9 years, and their separation varies between 11 and 36 astronomical units over that cycle. In 2012, researchers announced the possible detection of a planet around Alpha Centauri b, but subsequent analysis cast doubt on that finding, and it is no longer considered confirmed. The question of whether the Alpha Centauri system hosts Earth-like planets remains open. Beyond Alpha Centauri, the next nearest stars form a short list of relatively close neighbors. Barnard's star, a red dwarf about 5.96 light-years away, is notable for having the largest proper motion of any star in the sky, meaning it moves against the background of more distant stars faster than any other known star, a result of its proximity and its actual velocity through space. In 2018, researchers reported evidence of a planet candidate around Barnard's star, though this too remains unconfirmed. Wolfram 359, at about 7.8 light-years, is another red dwarf, perhaps best known in popular culture as the location of a fictional battle in a television series. Leyland 21, 185, Sirius, Leuchten 7268, Ross 154. The nearest stellar neighbors form a sparse community of mostly dim red dwarfs, with the occasional brighter sun-like star scattered among them. Within 10 light-years of Earth, there are thought to be roughly 10 to 12 star systems, containing perhaps 15 to 20 individual stars in total. 10 light-years. That is the neighborhood. And even within this tiny corner of the Milky Way, the distances are staggering. Traveling to Barnard's star at the speed of Voyager, one would take approximately 145,000 years. Reaching Sirius at 8.6 light-years would take roughly 150,000 years by the same measure. These numbers are not meant to discourage. They are meant to establish an honest baseline. Because before we can discuss how we might ever close these distances, we need to understand exactly how far they are and why our current methods fall so dramatically short. 1 light-year, then, is the distance that sits between us and the edges of our solar system's most diffuse outer reaches on one side and the nearest stars on the other. It is a distance that no human technology has ever come close to crossing. It is a distance that, as we will see, would require either speeds we cannot currently achieve, timescales that dwarf all of recorded history, or engineering concepts that remain entirely theoretical. Chapter 7: Human Spacecraft Today. Let us be precise about where we stand. How fast can we actually go? What are the fastest spacecraft humanity has ever built? And what do their speeds tell us about the challenge of crossing even a fraction of a light year? The answer requires separating a few different categories of speed. There is the speed of a spacecraft relative to the Earth at launch. There is its speed relative to the Sun. And there is its speed relative to the target, which may itself be moving. For our purposes, the most relevant figure is speed relative to the Sun, since that is what determines how quickly a spacecraft moves through the solar system and out into interstellar space. Voyager 1, as we have noted, travels at approximately 17 kilometers per second relative to the Sun. This makes it the fastest human-made object currently in interstellar space. But it was not the fastest spacecraft at the moment of its launch. It achieved much of its velocity through a technique called a gravitational assist, or gravity slingshot, using the gravitational fields of Jupiter and Saturn to accelerate without burning additional fuel. The gravitational assist is one of the most elegant techniques in spaceflight. When a spacecraft approaches a massive planet, it falls into the planet's gravitational field and accelerates. If the geometry is right, the spacecraft can swing around the planet and leave in a new direction with more speed than it arrived with. The planet loses an infinitesimally tiny amount of momentum in the exchange, an amount so small as to be utterly negligible on any practical scale. The spacecraft gains speed essentially for free, limited only by the geometry of the trajectory and the mass of the planet. Voyager 1's flyby of Jupiter in March of 1979 and Saturn in November of 1980 gave it the velocity it needed to escape the solar system entirely. Without those assists, it would have needed far more propellant to reach its current speed. New Horizons, launched in 2006, was the fastest spacecraft ever launched from Earth at the time of its departure, leaving with a velocity of about 16.26 kilometers per second relative to Earth. After a gravitational assist from Jupiter, it reached its maximum speed of about 23 kilometers per second at its closest approach to the Sun, then gradually slowed as it climbed away from the Sun's gravitational pull. Its current speed in the outer solar system is about 14 kilometers per second. But both of these spacecraft are slow by the standards of what physics permits. The real speed records belong to probes that have passed close to the Sun, where they can exploit the Sun's far greater gravity for acceleration. The Parker Solar Probe, launched in 2018 with the mission of studying the Sun's outer atmosphere, has used a series of Venus gravity assists to progressively lower its perihelion, the closest point of its orbit to the Sun. In late 2024, it made its closest approach yet, passing within about 6.1 million kilometers of the solar surface. At that point, it was moving at approximately 692,000 kilometers per hour, or about 192 kilometers per second. 192 kilometers per second. That is more than 11 times faster than Voyager 1. It sounds like a significant improvement, and in absolute terms it is, but expressed as a fraction of the speed of light, it is still only about 0.064%. The Parker Solar Probe The fastest human-made object ever at the time of its record was moving at about 1/1500th of the speed of light. At 192 kilometers per second, traveling in a straight line at constant speed, it would take approximately 15,000 years to cross 1 light year. That is still a geological timescale. That is longer than the entirety of human civilization. And of course, the Parker Solar Probe only reaches that speed at its closest approach to the Sun. It is not maintaining that velocity continuously. It is not heading out of the solar system. It is in an elliptical orbit that brings it repeatedly close to the Sun and then swings it back out. To use that speed for an interstellar mission, you would need a fundamentally different kind of mission architecture. The current generation of chemical rockets, the kind that have powered every crewed mission in history, are limited by the energy density of their propellants. The best chemical propellants available, liquid hydrogen and liquid oxygen, produce a specific impulse, a measure of fuel efficiency, of around 450 seconds. This is close to the theoretical maximum for chemical propulsion. Chemical rockets are excellent for launching payloads from Earth's surface into orbit, but they are deeply unsuited for interstellar travel. The amount of propellant required to accelerate a spacecraft to even a small fraction of the speed of light using chemical propulsion would be absurdly, impossibly large. Ion propulsion offers a significant improvement in efficiency, though at the cost of thrust. Ion engines work by ionizing a propellant, usually xenon gas, and accelerating the ions using electric fields to produce thrust. They produce very little force at any given moment, far less than a chemical rocket, but they can operate continuously for months or years, gradually building up speed with extraordinary fuel efficiency. The Dawn spacecraft, which orbited both the asteroid Vesta and the dwarf planet Ceres, used ion propulsion and achieved a total change in velocity over its mission of about 11.5 kilometers per second, more than any other spacecraft propulsion system has ever delivered. But even ion propulsion, in its current form, falls far short of what interstellar travel would require. The speeds achievable with near-term ion technology are still measured in tens of kilometers per second at best. Crossing 1 light year in a human lifetime would require speeds on the order of tens of thousands of kilometers per second, or several percent of the speed of light. That is 2 to 3 orders of magnitude beyond what our best current systems can deliver. This is the honest picture of where we stand. Our fastest spacecraft move at speeds that would take them thousands to tens of thousands of years to cross a single light year. Our most efficient propulsion systems are still many orders of magnitude short of what interstellar travel demands. The gap between where we are and where we would need to be is not a small gap. It is one of the largest engineering challenges our species has ever contemplated. Chapter 8. The Physics of Going Faster. Given the gap between our current capabilities and what interstellar travel requires, the natural question is, what would it actually take to go faster? Is it simply a matter of building better engines, or are there fundamental physical limits that constrain us regardless of our engineering? The answer is both. There are practical engineering constraints that we might overcome with sufficient time and resources, and there are fundamental physical limits that we cannot overcome, no matter how advanced our technology becomes. Understanding the difference between these two categories is essential for thinking clearly about the future of space travel. Let us start with the engineering side. The fundamental challenge of accelerating a spacecraft to high speeds is captured by what rocket scientists call the Tsiolkovsky rocket equation. formulated by the Russian mathematician Konstantin Tsiolkovsky in 1897. The equation describes the relationship between a rocket's exhaust velocity, the mass of the propellant it carries, and the final change in velocity it can achieve. The rocket equation has a deeply inconvenient property. The relationship between propellant mass and final velocity is not linear. It is exponential. As you try to achieve higher and higher velocities, the amount of propellant required grows not proportionally, but explosively. To double your final velocity, you do not need twice as much propellant. You need much more than twice as much. To illustrate the problem, consider a spacecraft trying to accelerate to 1% of the speed of light, approximately 3,000 kilometers per second, using a hypothetical rocket with an exhaust velocity of 100 kilometers per second, which is already far beyond anything we have built. The rocket equation tells us that the ratio of propellant mass to final spacecraft mass would need to be approximately 10 to the power of 13. That is 10 trillion kilograms of propellant for every kilogram of final spacecraft. The numbers are not just impractical, they are physically absurd. This is why rocket engineers talk about the tyranny of the rocket equation. Chemical and even nuclear thermal rockets are fundamentally limited by the velocity at which they can expel their exhaust. No matter how efficiently you burn your propellant, you cannot get around the fact that you have to carry all that propellant with you from the start, and propellant has mass, and mass requires more propellant to accelerate it, which adds more mass, which requires more propellant, in a cycle that quickly becomes unmanageable at the velocities interstellar travel demands. One partial solution to this problem is to not carry your propellant at all. The solar sail concept exploits the radiation pressure of sunlight to accelerate a spacecraft without any propellant whatsoever. Light exerts a tiny but real force on any surface it strikes, and if that surface is large enough and light enough, the cumulative effect of that force over time can produce significant acceleration. A solar sail large enough and close enough to the Sun could, in principle, reach speeds of hundreds of kilometers per second. The limitation of solar sails driven by sunlight is that the force of sunlight diminishes with the square of the distance from the Sun. As a solar sail moves away from the Sun, the acceleration it receives drops rapidly. It would receive most of its total velocity boost in the first few days or weeks of the mission, while still close to the Sun. After that, it would coast at whatever speed it had accumulated. A more powerful variant of this idea uses a laser instead of sunlight. Rather than relying on the Sun's diffuse radiation pressure, a ground-based or space-based laser array would beam focused light at the sail continuously, providing a sustained and much more powerful acceleration. This is the basic idea behind the Breakthrough Starshot initiative, which we will discuss in more detail in a later chapter. Nuclear propulsion represents another route toward higher velocities. There are several variants. Nuclear thermal propulsion heats a propellant, typically liquid hydrogen, using a nuclear reactor, and expels it through a nozzle. This can achieve specific impulse values roughly twice as high as the best chemical rockets, meaning it uses propellant about twice as efficiently. Several nuclear thermal rocket designs were tested during the 1960s and 70s under programs like NERVA in the United States, and the technology is considered feasible with relatively modest development effort. But even nuclear thermal propulsion, while significantly better than chemical rockets, still falls far short of the velocities needed for interstellar travel within human timescales. Nuclear pulse propulsion is a more radical concept. The most developed version, known as Project Orion, was studied seriously in the United States in the late 1950s and early 1960s. The idea involves detonating a series of nuclear explosives behind a spacecraft, using the blast to push a large pusher plate, which then transfers the impulse to the spacecraft through a system of shock absorbers. Studies suggested that an Orion-type spacecraft could potentially achieve velocities of several % of the speed of light if scaled up sufficiently. The concept was never built, partly due to the political and environmental concerns surrounding nuclear explosions in space, and partly due to the sheer complexity and cost of the engineering. A more refined variant called nuclear pulse propulsion, using fusion micro-explosions, sometimes called Project Daedalus or Project Icarus, depending on the specific study, has been explored by the British Interplanetary Society and other organisations. These designs propose using small fusion reactions, triggered by lasers or particle beams, to provide a sustained series of high-energy pulses. Theoretical studies suggest that such a system could potentially accelerate a large robotic probe to perhaps 5 to 12% of the speed of light, which would make a journey to Proxima Centauri possible in roughly 40 to 80 years. These designs remain entirely theoretical and would require engineering capabilities well beyond our current level, but they are not obviously impossible in principle. Beyond nuclear propulsion, there is the concept of antimatter propulsion. When matter and antimatter meet, they annihilate each other completely, converting 100% of their mass into energy, according to Einstein's famous equation. This is the most energy-dense reaction physically possible. A matter-antimatter rocket would, in principle, be able to achieve velocities approaching a significant fraction of the speed of light, with a far smaller propellant mass than any other propulsion concept. The problems are formidable. Producing antimatter requires enormous amounts of energy, far more than the antimatter itself contains. Storing antimatter safely for extended periods is an unsolved engineering challenge, and the engineering of an engine that could handle the annihilation reaction at the scale needed for propulsion does not yet exist. But antimatter propulsion remains a theoretically coherent concept, and it represents one of the upper bounds of what might be achievable within the laws of physics as we currently understand them. There is also a category of concepts that go beyond conventional rocketry entirely. Ideas like the Bussard ramjet, which would scoop interstellar hydrogen as it travelled and use it as fuel for fusion reactions, eliminating the need to carry propellant at all. This concept, proposed by physicist Robert Bussard in 1960, captured considerable imaginative attention, but has faced serious theoretical challenges. The density of interstellar hydrogen is so low that the drag from scooping it might exceed the thrust gained from burning it, and the engineering of the magnetic scoop required would be extraordinary. The ramjet remains an interesting idea, but not a currently viable one. And then there are the truly speculative possibilities: wormholes, warp drives, and other exotic space-time manipulations suggested by general relativity. We will not dwell on these here, because they require either exotic matter with properties that may not exist in nature, or energy scales so far beyond anything imaginable that they serve more as thought experiments than engineering proposals. The honest assessment is that if faster-than-light travel, or its effective equivalent, is ever achieved, it will require physics we do not yet understand. Within the physics we do understand, the ceiling for conventional rocket propulsion is set by the rocket equation and the energy density of available fuels. The ceiling for light sail or laser sail propulsion is set by the power of the available laser, array, and the reflectivity and durability of the sail material. The ceiling for nuclear propulsion concepts is set by the efficiency of the nuclear reactions and the engineering of the drive system. None of these ceilings, as far as we can currently tell, permit speeds much above perhaps 20 to 30% of the speed of light, and achieving even that would require engineering effort on a scale that dwarfs anything humanity has ever undertaken. Chapter 9. Relativistic Travel. There is a point at which the physics of space travel stops being merely an engineering problem and becomes something stranger and more fundamental. That point is reached when a spacecraft begins to approach a meaningful fraction of the speed of light. At those velocities, the everyday rules of motion that we inherit from Newton no longer tell the complete story. A different framework takes over, one developed by Albert Einstein in the early 20th century, and its consequences are among the most counterintuitive in all of science. Einstein's special theory of relativity, published in 1905, begins with two postulates. The first is that the laws of physics are the same for all observers moving at constant velocity relative to one another. The second is that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these two simple statements, an entire architecture of surprising consequences follows. The most famous of these consequences is the equivalence of mass and energy, expressed in the equation that relates energy to mass, multiplied by the square of the speed of light. But for our purposes, the most relevant consequences are two phenomena known as time dilation and length contraction. Time dilation is the slowing of time experienced by an object moving at high velocity relative to a stationary observer. The effect is real, measurable, and has been confirmed by numerous experiments. It is not an illusion or an artifact of measurement. Moving clocks genuinely run slow relative to clocks at rest. The faster you move, the more pronounced the effect becomes. At everyday speeds, the effect is negligibly small. A commercial aircraft traveling at 900 kilometers per hour experiences time dilation of about 1 part in 10 trillion relative to the ground. Over a full year of flight, the difference in elapsed time would be only a few nanoseconds. GPS satellites, which orbit at about 14,000 kilometers per hour, experience a more significant effect, and their onboard clocks must be corrected for both special relativistic time dilation and the gravitational time dilation described by general relativity to keep them synchronized with ground clocks. But as speeds approach a significant fraction of the speed of light, the effect becomes dramatic. At 50% of the speed of light, a moving clock runs at about 87% of the rate of a stationary clock. At 90% of the speed of light, it runs at about 44% of the stationary rate. At 99%, it runs at about 14%. At 99.9%, it runs at about 4.5%. The closer you get to the speed of light, the more severely time slows for the traveler relative to someone left behind. This has a profound implication for interstellar travel. A spacecraft traveling at 99% of the speed of light would take approximately 4.3 years to reach Proxima Centauri, as measured by an observer on Earth. But for the crew on board, the journey would feel much shorter, only about 7 months, because their clocks are running at roughly 14% of the Earth rate. At 99.9% of the speed of light, the crew would experience only a few weeks of travel time, while 4.3 years passed on Earth. In principle, this means that a sufficiently fast spacecraft could traverse enormous distances within a single human lifetime, as experienced by the crew. A spacecraft traveling at very close to the speed of light could, in principle, cross the entire observable universe within a human lifetime as experienced by the traveler, while billions of years passed for the rest of the universe. The traveler would return, if return were possible, to find everyone they had ever known long dead. The stars shifted. The universe unrecognizably aged. Time dilation is sometimes presented as a loophole in the apparent impossibility of interstellar travel, and in a sense it is for the traveler. But it does not solve the problem of communication or return. Any civilization that sent travelers to the stars at near light speed would be committing to a one-way relationship with those travelers. Messages sent back would take years to arrive. The travelers who returned would be returning to a world that had aged far beyond anything they had known. The companion phenomenon to time dilation is length contraction. From the perspective of a traveler moving at high velocity, distances in the direction of travel appear compressed. At 99% of the speed of light, a distance of 4.24 light-years, the gap between Earth and Proxima Centauri, would appear to the traveler as only about 0.6 light-years. At 99.9%, it would appear as only about 0.13 light-years. The universe, from the perspective of a near light-speed traveler, shrinks in the direction of motion. This is not a perceptual trick. It is a genuine geometric consequence of the way space and time are structured at relativistic velocities. Space and time are not separate, fixed quantities. They are aspects of a unified four-dimensional structure called space-time, and the way that structure is measured depends on the observer's state of motion. There is another relativistic effect that matters enormously for practical interstellar travel: the increase of effective mass with velocity. As an object accelerates toward the speed of light, the energy required to accelerate it further increases without limit. An object with any rest mass at all would require infinite energy to reach exactly the speed of light. This is why the speed of light is an absolute speed limit for any object with mass. It is not a technical barrier. It is a mathematical certainty embedded in the structure of space-time. This means that any spacecraft carrying passengers must travel below the speed of light. The question is how far below and what the practical implications are. At 10% of the speed of light, relativistic effects are still fairly small, and the journey to Proxima Centauri would take about 43 years, as experienced by both the travelers and people on Earth. At 50%, the journey takes about 9 years for both. At 90%, it takes about 4.7 years for Earth observers and about 2 years for the crew. These are still long journeys, but they are not geological timescales. They are timescales within human experience, at least for the crew. The question is whether we could ever build a spacecraft capable of achieving those velocities. And that brings us back to the engineering constraints we discussed in the previous chapter. There is one additional relativistic complication worth noting: the problem of collisions at high speed. At 10% of the speed of light, a spacecraft would be moving at approximately 30,000 kilometers per second. At that velocity, a collision with even a speck of dust could release energy comparable to a nuclear weapon. The interstellar medium, while extremely diffuse, is not perfectly empty. Hydrogen atoms, dust grains, and larger particles are present throughout. A spacecraft traveling at relativistic speeds would need either extraordinary shielding, some form of active particle deflection, or a route through unusually empty space. This is not an insurmountable problem in principle, but it is a serious engineering challenge that is often understated in popular discussions of interstellar travel. Relativity, then, offers both a gift and a constraint. The gift is time dilation, the possibility that interstellar distances could be traversed within a human lifetime. From the traveler's perspective, if sufficiently high speeds could be achieved. The constraint is the speed limit itself, along with the steeply rising energy costs as that limit is approached. A universe in which the speed of light is finite and constant is a universe in which interstellar travel is possible in principle, but extraordinarily demanding in practice. Chapter 10. Proposed propulsion concepts. We have established that our current spacecraft are too slow for interstellar travel by many orders of magnitude, and we have examined the physical constraints that make going faster so demanding. Now let us look at the specific propulsion concepts that scientists and engineers have seriously proposed as potential paths toward interstellar velocities. These range from near-term technologies that could be deployed within decades to far future concepts that would require civilizational scale engineering effort. The most immediately promising concept for achieving a fraction of the speed of light with current or near-term technology is the laser sail. The basic principle is elegant. A thin reflective sail attached to a small spacecraft is illuminated by a powerful laser array. The radiation pressure of the laser light accelerates the sail. Because the spacecraft carries no propellant, it is not subject to the tyranny of the rocket equation. Its final speed is determined by the power of the laser, the mass of the sail and payload, and the duration of the laser illumination. The Breakthrough Starshot initiative, announced in 2016 by the billionaire entrepreneur Yuri Milner, and backed by a group of prominent scientists including the late Stephen Hawking, proposed sending a fleet of gram-scale spacecraft, each carrying a tiny sensor package, camera, and communications system, to the Alpha Centauri system using exactly this principle. The proposal called for a laser array of roughly 100 gigawatts of power, illuminating sails of a few meters in diameter for a few minutes. The resulting acceleration would be extraordinary, roughly 10,000 times the acceleration due to gravity on Earth's surface, and the spacecraft would reach about 20% of the speed of light within minutes of launch. At 20% of the speed of light, the journey to Alpha Centauri would take approximately 20 to 25 years. The spacecraft would fly through the system without stopping, since there is no way to decelerate without a similar laser array at the destination, and would transmit data back to Earth for several years after the flyby, with signals taking 4.2 years to arrive. Breakthrough Starshot faces enormous engineering challenges. The sail material must be extraordinarily thin, reflective, and thermally resistant to withstand the intense laser illumination without being destroyed. The electronics must be miniaturized to gram scale while remaining functional. The laser array would need to be built in space, and keeping it precisely focused on a tiny sail over a distance of thousands of kilometers would require extraordinary precision. The cost of the laser array alone would likely run to tens of billions of dollars at minimum. None of these problems are considered physically impossible, but each represents a formidable engineering challenge. Nevertheless, Breakthrough Starshot has attracted serious scientific attention and ongoing research funding. It represents the most concrete and technically grounded proposal for achieving interstellar velocities with near-future technology. For larger spacecraft carrying human passengers, laser sails are less practical. The sail area required to accelerate a human-carrying spacecraft to even a few % of the speed of light using a feasible laser array would be enormous, and the structural challenges of building and deploying such a sail are considerable. For crewed interstellar missions, attention turns to nuclear propulsion concepts. Nuclear thermal propulsion, as mentioned in the previous chapter, uses a nuclear reactor to heat propellant to high temperatures and expel it through a nozzle. It offers roughly twice the efficiency of chemical rockets and could be developed with relatively modest investment compared to more exotic options. Several space agencies and private organizations have renewed interest in nuclear thermal propulsion for missions to Mars and the outer solar system. For interstellar missions, it falls short, but it represents a realistic near-term improvement over chemical propulsion. Nuclear pulse propulsion, particularly the Orion concept, remains perhaps the most thoroughly studied high-performance propulsion concept in history. Project Orion was studied seriously by physicists, including Freeman Dyson, in the late 1950s and early 1960s. A large Orion-type spacecraft, using thousands of nuclear pulse units, was calculated to be capable of reaching several percent of the speed of light. Dyson himself estimated that a ship massive enough to carry a significant crew and supplies could reach Alpha Centauri in roughly 130 years using nuclear pulse propulsion, though more optimistic estimates with larger designs pushed that figure lower. The Daedalus project, studied by the British Interplanetary Society in the 1970s, proposed an unmanned fusion pulse spacecraft that would reach Barnard's star in about 50 years, traveling at approximately 12% of the speed of light. The design used pellets of deuterium and helium-3, ignited by electron beams in a large reaction chamber. The helium-3 fuel posed a particular challenge, as it is extremely rare on Earth, and the study proposed mining it from the atmosphere of Jupiter. Project Icarus, a more recent successor study begun in 2009, has explored updated versions of the Daedalus concept with modern engineering approaches. Fusion propulsion more broadly represents one of the most promising long-term paths toward interstellar-class velocities. A successful fusion rocket could achieve specific impulse values, orders of magnitude higher than chemical or nuclear thermal rockets, potentially enabling spacecraft velocities of 10 to 20% of the speed of light. The challenge is that controlled fusion has proven extraordinarily difficult to achieve even for stationary power generation, let alone for a propulsion system. Significant progress has been made in recent years, and the prospect of commercial fusion power within the coming decades has improved. But the translation from a terrestrial fusion reactor to a spacecraft propulsion system involves many additional engineering steps. Antimatter propulsion represents the theoretical pinnacle of rocket-based propulsion within known physics. A perfect matter-antimatter annihilation rocket, converting 100% of its fuel mass to energy, could in principle achieve velocities approaching 90% of the speed of light or higher. The energy density of antimatter is approximately 10 billion times higher than chemical fuels and about 1,000 times higher than nuclear fission. A mission to Alpha Centauri taking 5 or 6 years of travel time would be theoretically feasible with antimatter propulsion. The barriers are immense. The total amount of antimatter produced by all the particle accelerators in the world over their entire operational histories amounts to a few nanograms. The energy cost of producing antimatter with current methods is approximately 10 billion times greater than the energy released when it annihilates. Storing antihydrogen requires sophisticated magnetic traps and cannot be maintained indefinitely. The engineering of an antimatter rocket engine does not currently exist even in theoretical design. But if the production and storage problems were ever solved, antimatter propulsion would be transformative. several other propulsion concepts occupy the space between near-term feasibility and far future speculation. Magnetohydrodynamic drives, which accelerate ionized plasma using magnetic fields, offer efficiency improvements over conventional ion engines. Solar thermal propulsion uses concentrated sunlight to heat a propellant. Microwave thermal propulsion uses beamed microwave energy instead of a laser. Electric sails, proposed by the Finnish scientist Pekka Janhunen, use a long conducting wire charged to a high voltage to deflect the solar wind and generate thrust without any propellant. Each of these concepts has particular strengths and weaknesses, and each represents a genuine area of ongoing research. None of them, in their current form, solves the interstellar travel problem. But taken together, they suggest a rich landscape of possibilities for the future of space propulsion, a landscape in which the fundamental physics permits a great deal more than our current engineering can deliver. Chapter 11. The Interstellar Medium. Between the stars, space is not quite empty. It is filled with a tenuous mixture of gas, dust, radiation, and magnetic fields that collectively make up the interstellar medium. Understanding what a spacecraft would encounter on an interstellar journey requires a careful look at this environment, because while the interstellar medium is extraordinarily diffuse by terrestrial standards, it presents real challenges for any object moving through it at high speed. The interstellar medium is roughly 99% gas and 1% dust by mass. The gas is predominantly hydrogen, with helium making up most of the remainder, and trace amounts of heavier elements scattered throughout. This hydrogen exists in several different forms depending on the local conditions. In dense, cold regions, it exists as molecular hydrogen, pairs of hydrogen atoms bonded together. In warmer regions, it exists as neutral atomic hydrogen. In regions heated by nearby stars or other energetic sources, it exists as ionized hydrogen, meaning the electrons have been stripped away from the protons, creating a plasma. The average density of the interstellar medium in our part of the galaxy is roughly 1 hydrogen atom per cubic centimeter. This is almost incomprehensibly sparse. A cubic centimeter of the air you are breathing now contains roughly 27 million trillion molecules. The interstellar medium contains just 1 atom in that same volume. For most purposes, the space between stars is a vacuum far more perfect than anything we can create in a laboratory on Earth. But a spacecraft traveling at a significant fraction of the speed of light does not experience even this extraordinarily thin medium as negligible. At 10% of the speed of light, the relative velocity between the spacecraft and the ambient hydrogen is 30,000 kilometers per second. Each hydrogen atom that the spacecraft encounters has a kinetic energy, in the spacecraft's reference frame, equivalent to that of a high-energy cosmic ray particle. The cumulative effect of billions of such encounters per second on the spacecraft's forward surface would cause gradual erosion of the material, a process called sputtering. Over the years or decades of an interstellar journey, this erosion could be significant. Dust grains pose an even greater hazard. The interstellar medium contains microscopic particles of silicate and carbon compounds ranging in size from a few nanometers to perhaps a micrometer. These particles are extremely sparse, but at interstellar velocities, a collision with even a micrometer-sized grain would release energy comparable to a small explosive. Studies of the breakthrough starshot concept have concluded that even gram-scale spacecraft would need some form of shielding or defensive strategy to survive the dust environment over a 20-year journey to Alpha Centauri. various shielding strategies have been proposed. A thin sacrificial layer of material on the spacecraft's leading face would absorb and ablate away gradually over the journey. A small cloud of gas maintained ahead of the spacecraft could vaporize incoming dust particles before they struck the hull. An active system using radar or LiDAR to detect incoming particles and maneuver to avoid them has also been suggested, though the velocities involved make real-time avoidance of small particles essentially impossible. Beyond gas and dust, the interstellar medium also contains cosmic rays, high-energy particles, mostly protons and atomic nuclei, accelerated to near-light speeds by supernova remnants, pulsars, and other energetic phenomena. The flux of cosmic rays in interstellar space is significantly higher than within the solar system, where the solar wind's magnetic field provides some shielding. A crew on an interstellar spacecraft would be exposed to elevated cosmic ray radiation throughout the journey, requiring substantial shielding for any crewed mission. The interstellar medium is not uniform. Our solar system currently resides in a region called the local bubble, a low-density cavity in the interstellar medium roughly 1,000 light-years across, thought to have been carved out by a series of supernova explosions over the past 10 to 20 million years. The density of the interstellar medium within the local bubble is significantly lower than average, roughly 1/10 to 1/100th of the typical interstellar density. In a sense, we are fortunate in our location. The immediate neighborhood of the solar system is among the less hostile regions of interstellar space. Beyond the local bubble, the interstellar medium becomes denser and more varied. Dense molecular clouds, where stars are born, can have densities millions of times higher than the average interstellar medium. Regions near supernova remnants are swept by expanding shells of hot plasma. The spaces between spiral arms of the galaxy are particularly empty, while the arms themselves contain higher concentrations of gas and dust. For a spacecraft traveling to Proxima Centauri, the journey would remain within the local bubble for its entire duration. The interstellar environment along that route is about as benign as interstellar environments get. The radiation environment would still be more intense than within the solar system, and the dust hazard at high velocities would still require careful engineering attention. But the overall density of material would be at the lower end of the interstellar range. There is one final aspect of the interstellar medium worth noting: its magnetic field. The galaxy is permeated by a weak magnetic field, with a strength of a few microgauss, orders of magnitude weaker than the Earth's surface field. This field influences the trajectories of charged particles, including cosmic rays, and it would interact with any magnetic systems aboard an interstellar spacecraft. It might also be exploited. The magnetic sail, concept proposed by Dana Andrews and Robert Zubrin in 1990, involves deploying a large superconducting loop that generates a magnetic field large enough to deflect the interstellar medium, creating a form of drag or thrust, depending on the relative motion of the spacecraft and the ambient plasma. The interstellar medium, then, is not the featureless void of popular imagination. It is a complex, structured environment with its own physics and its own hazards. Any serious engineering of an interstellar mission must account for it carefully, from the shielding of the forward surface against grain impacts and radiation, to the design of systems that can operate reliably in the presence of elevated cosmic ray flux, to the long-term maintenance of spacecraft integrity over journeys of decades or longer. Chapter 12. generation ships, and deep time. All of the propulsion concepts we have discussed so far share a common ambition: to reduce the travel time to the stars to something within a human lifetime, or at least within a few generations. But there is another approach entirely, one that does not try to go fast at all, but instead accepts the vast timescales involved and asks what kind of vessel and what kind of society could survive the journey regardless of how long it takes. This is the concept of the generation ship, sometimes also called a world ship or a multi-generational vessel. The idea is simple in outline, though staggering in its implications. Build a spacecraft large enough to be a self-contained habitat, capable of supporting a population of human beings indefinitely. Launch it toward the nearest stars at whatever speed current technology permits. The people who arrive will not be the people who left. They will be the descendants, perhaps dozens or hundreds of generations removed, of the original crew. At Voyager, one's current speed of 17 kilometers per second, a journey to Proxima Centauri would take approximately 73,000 years. That is not dozens of generations. That is thousands of generations. Even at the more optimistic speeds achievable with near-term nuclear propulsion, perhaps a few hundred kilometers per second, a journey to the nearest star would take tens of thousands of years. The generation ship concept, taken seriously, implies civilizations living and dying entirely within a metal vessel traveling through the void, with no planet underfoot and no star overhead, except as a distant point of light, growing imperceptibly brighter over centuries. The engineering requirements for a true generation ship are almost beyond current comprehension. The vessel would need to be large enough to support a viable human population, which ecologists and population geneticists generally estimate as requiring at minimum a few hundred individuals to maintain genetic diversity over long timescales, and more realistically, several thousand. It would need to produce its own food, recycle all air and water, generate its own energy, and maintain all of its systems without external support for tens of thousands of years. The materials science alone presents extraordinary challenges. No material we currently know of maintains structural integrity over those timescales without maintenance. Metals fatigue, polymers degrade, electronics fail. The concept of a machine operating reliably for 10,000 years, let alone 70,000, requires either continuous maintenance and replacement by the inhabitants, or the development of self-repairing materials and systems far beyond our current capabilities. The social and psychological dimensions are equally challenging. What kind of culture, what kind of governance, what kind of educational system could maintain the knowledge and motivation to operate a complex spacecraft over hundreds of generations? There is no historical precedent for an institution that has maintained consistent purpose and organizational coherence over even a few thousand years, let alone tens of thousands. Religions, empires, languages, and cultures all change profoundly over such timescales. The idea that a human society could maintain the technical knowledge and collective will to continue a journey whose purpose was decided by distant ancestors, whose destination will never be seen by the living, and whose endpoint lies beyond any human memory of a beginning, is a profound challenge to our understanding of social continuity. Some researchers have proposed that the solution lies in the passengers not being awake for the journey. Suspended animation or cryonic preservation would allow travelers to be placed in a state of metabolic suspension and revived upon arrival, effectively removing the generational problem. The ship would carry sleeping passengers rather than living generations. The practical challenges are significant. No currently known technique for suspending human metabolism is reversible for more than a few hours in medical contexts, and the extension of this concept to decades or centuries of preservation faces formidable biological and engineering obstacles. But the idea is not obviously forbidden by physics, and it remains an active area of research in the context of both space travel and medicine. A related concept is the embryo ship. Rather than carrying adult passengers or even living generations, the spacecraft would carry frozen embryos and the robotic systems necessary to gestate and raise them upon arrival. This dramatically reduces the mass and resource requirements of the spacecraft, since frozen embryos take up almost no space or energy. The ship would be largely automated, with AI systems responsible for navigation and maintenance. Upon arrival at the destination, the robotic nursery systems would thaw and gestate a founding population, raise the resulting children, and educate them in the skills needed to establish a colony. The profound ethical and social questions raised by this scenario, including what it means to be born into a world entirely designed by and for you, with no living connection to a human past, are as interesting as the engineering challenges. The generation ship concept, whatever form it takes, ultimately forces us to confront the relationship between human timescales and cosmic ones. The universe operates on timescales that dwarf human experience. Stars live for billions of years. Galaxies evolve over hundreds of millions of years. Even the distances between the nearest stars, crossed at the speed of our fastest current spacecraft, require timescales longer than human civilization has existed. In this context, the generation ship is perhaps less a practical proposal than a thought experiment about the limits of human ambition. It asks whether our species is capable of committing to a project whose fruition lies beyond any individual human life, beyond any living memory, beyond any continuous institutional memory. Whether the answer is yes or no tells us something important about what kind of civilization we are and what kind we might become. Chapter 13. Exoplanets and Destinations. Even if we could cross the distance to another star, we would want to know something about what awaits us there. The question of whether nearby star systems contain habitable planets is not merely academic. It shapes the entire framing of interstellar travel, transforming it from a journey into the void to a journey towards somewhere specific. For most of human history, the existence of planets around other stars was entirely unknown. It seemed likely, given the vast number of stars in the universe, but likelihood is not the same as knowledge. The first confirmed detection of a planet orbiting a Sun-like star came in 1995, when Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of a planet orbiting the star 51 Pegasi using the radial velocity method. This technique detects the slight wobble that an orbiting planet induces in its host star as both objects orbit their common center of mass. The discovery earned Mayor and Queloz the Nobel Prize in Physics in 2019. Since then, the field of exoplanet research has expanded at extraordinary speed. The Kepler Space Telescope, launched by NASA in 2009 and operational until 2018, surveyed approximately 500,000 stars for transiting planets, those that pass in front of their host star from our line of sight, causing a tiny periodic dimming. Kepler confirmed the existence of more than 2,700 exoplanets and identified thousands more candidates. Its successor, the TESS mission, launched in 2018, continues this survey with coverage of a much larger area of sky. The statistical picture that has emerged from these surveys is remarkable. Exoplanets are not rare or exotic. They appear to be the norm. Nearly every star in the galaxy is likely to host at least one planet, and a significant fraction host multiple planets. Estimates suggest that the Milky Way contains somewhere between 100 billion and 400 billion planets. Rocky, Earth-sized planets in the habitable zones of their host stars, once thought to be perhaps rare, appear to be common. Within the nearest stellar neighborhood, the candidate list for potentially interesting destinations has grown steadily. We have already discussed Proxima Centauri b, the roughly Earth-sized planet in the habitable zone of our nearest stellar neighbor. Its habitability remains uncertain, but its existence is one of the most significant discoveries in recent astronomical history. The TRAPPIST-1 system, located about 40 light-years from Earth, contains 7 known Earth-sized planets, 3 of which orbit in the habitable zone of their small red dwarf host star. The system was studied intensively with the James Webb Space Telescope beginning in 2022, and while initial results have not confirmed liquid water or biological signatures, the system remains one of the most scientifically interesting nearby planetary systems known. Tau Ceti, a Sun-like star about 12 light-years from Earth, shows evidence of multiple planets, with at least 2 candidates in or near the habitable zone. Tau Ceti has long been regarded as one of the more promising targets for the search for extraterrestrial intelligence, and it remains an interesting destination from the perspective of interstellar exploration. Epsilon Eridani, about 10.5 light-years away, is a younger, slightly smaller star than the Sun, with a known debris disk, suggesting ongoing planetary formation or early solar system evolution. A Jupiter-like planet has been detected in the system, though the existence of smaller, potentially habitable worlds remains unconfirmed. The James Webb Space Telescope has begun the work of characterizing the atmospheres of some exoplanets, searching for signs of water vapor, carbon dioxide, methane, and other molecules. The detection of biosignatures, chemical signs of life in the atmosphere of a nearby exoplanet would transform the urgency of the interstellar travel discussion more profoundly than almost any other scientific discovery imaginable. We are not yet at that point, but the tools to make such a detection are either in place or within reach. What does all of this mean for the question of travel to the nearest stars? It means that the nearest stellar neighborhood is not a random collection of destinations. It is a set of specific, increasingly well-characterized star systems, some of which we have reason to believe may harbor rocky planets in conditions that could, under some circumstances, be favorable to life. The destination is not just empty space. It is potentially another world. This shifts the framing of interstellar travel in an important way. The question is no longer purely abstract, purely a matter of physics and engineering divorced from any concrete purpose. If Proxima Centauri b is confirmed to be habitable, or if a biosignature is detected in the atmosphere of a planet in the TRAPPIST-1 system, the motivation for crossing those distances becomes something other than pure exploration. It becomes contact. It becomes the possibility of knowing, beyond any doubt, that life is not unique to Earth. Even in the absence of such a discovery, the knowledge that rocky planets exist around nearby stars gives the interstellar travel question a concreteness it previously lacked. We are not contemplating a journey into an unknown void. We are contemplating a journey towards specific places with specific properties that we are learning about in ever greater detail. Chapter 14. The Scale of the Galaxy. We have spent much of this video focused on the relatively modest distance of 1 light-year and on the nearest stellar neighborhood within a few light-years of Earth. Now let us step back considerably and consider these distances in the context of the galaxy as a whole, because 1 light-year, for all the challenge it represents to human travel, is an almost negligibly small unit at the scale of the Milky Way. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped region of stars from which several spiral arms extend outward. Its disk has a diameter of roughly 100,000 light-years, and its total thickness is perhaps 1,000 light-years in most regions, thickening toward the center. The Sun is located approximately 26,000 to 28,000 light-years from the galactic center, roughly 2/3 of the way out from the center to the edge of the disk, in a relatively calm region between 2 major spiral arms, sometimes called the Orion Spur or the Local Arm, 100,000 light-years. At the speed of Voyager 1, crossing the Milky Way from one edge to the other would take approximately 1.8 billion years. That is longer than the time that has elapsed since complex multicellular life appeared on Earth. At the speed of the Parker Solar Probe at its fastest, it would still take about 16 million years. Even at 10% of the speed of light, crossing the galaxy would require 1 million years. The galaxy contains an estimated 100 to 400 billion stars. If you were to represent each star in the Milky Way as a single grain of sand, you would need somewhere between a large bathtub and a small swimming pool full of sand. Most of those stars are red dwarfs, dim and long-lived, burning their hydrogen slowly over timescales of tens to hundreds of billions of years. Sun-like stars, those similar to our own in mass and luminosity, make up roughly 10% of the total. The distribution of stars in the galaxy is not uniform. The central bulge, a roughly spherical region around the galactic center, contains an older, denser population of stars. The spiral arms contain younger stars, star-forming regions, and higher concentrations of gas and dust. The disk is populated by a mix of stellar ages, with older stars generally occupying orbits that stray further above and below the galactic plane. A diffuse spherical halo of ancient stars surrounds the disk, along with globular clusters, dense balls of tens of thousands to millions of stars that orbit the galaxy at large distances. At the center of the Milky Way lies a supermassive black hole known as Sagittarius A star, with a mass of approximately 4 million times that of the Sun. Its presence is inferred from the orbits of stars in the galactic center region, which move at speeds of thousands of kilometers per second around an invisible central mass, orbits that make sense only if that mass is concentrated within a region smaller than our solar system. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, showing the characteristic bright ring of heated material surrounding the black hole's shadow. The nearest large galaxy to the Milky Way is the Andromeda Galaxy, also known as Messier 31, located approximately 2.5 million light-years away. Andromeda is a spiral galaxy similar in many respects to the Milky Way, though somewhat larger, with perhaps 1 trillion stars compared to our galaxy's estimated 100 to 400 billion. It is visible to the naked eye from a dark location as a faint smudge of light in the constellation Andromeda, and it is the most distant object routinely visible without optical aid. Andromeda is currently approaching the Milky Way at approximately 110 kilometers per second. in approximately 4 to 5 billion years, the two galaxies are expected to begin a merger process, eventually combining into a single, larger elliptical galaxy. The Sun will likely still exist at that point, though it will be nearing the end of its main sequence life. The merger will not destroy the solar system directly, since the stars in both galaxies are so far apart that actual stellar collisions are extremely unlikely. But it will dramatically reshape the structure of both galaxies and scatter stars into new orbits over a period of hundreds of millions of years. The local group, the collection of galaxies to which both the Milky Way and Andromeda belong, contains roughly 80 galaxies in total, most of them small dwarf galaxies orbiting the two larger spirals. The local group itself spans about 10 million light-years. Beyond the local group, galaxies are organized into larger clusters and superclusters. The Virgo cluster, the nearest major galaxy cluster, is about 54 million light-years away and contains over 1,000 individual galaxies. The local group is falling toward the Virgo cluster under gravity at several hundred kilometers per second, a journey that will take billions of years to complete. 1 light-year, in this context, is a unit so small as to be almost meaningless at galactic scales. It is the width of a single hair, measured against the length of a continent. The challenge of crossing 1 light-year, which we have explored in such detail throughout this video, is the challenge of crossing the smallest meaningful unit of interstellar space, the gap between neighboring stars, not the galaxy, not the universe, just one step from one stellar system to the next. And yet that one step is, as we have seen, an almost incomprehensible engineering challenge with current technology. The scale of the galaxy is not something we can meaningfully aspire to cross. It is something we can only contemplate from our small vantage point on a rocky world orbiting an unremarkable star, 2/3 of the way out from the center of an average spiral galaxy, in a quiet corner of an enormous universe. Chapter 15. The Observable Universe. Beyond our galaxy, beyond the local group, beyond the Virgo cluster and its surrounding supercluster, the universe extends to distances so vast that the light-year itself begins to feel inadequate as a unit. Astronomers dealing with cosmological distances often switch to megaparsecs, each of which equals about 3.26 million light-years, simply because the light-year becomes an unwieldy unit at the scales involved. The observable universe is the portion of the total universe from which light has had time to reach us since the Big Bang, approximately 13.8 billion years ago. Because light travels at a finite speed, there is a horizon beyond which we cannot see, not because nothing exists there, but because the universe has not existed long enough for light from those regions to have reached us yet. You might expect the observable universe to extend 13.8 billion light-years in every direction, since that is how long light has been traveling. But the actual radius of the observable universe is considerably larger, approximately 46.5 billion light-years, giving it a diameter of about 93 billion light-years. The reason for this apparent discrepancy is that the universe has been expanding throughout its history. The galaxies whose light we see today were much closer to us when that light was emitted, but they have since moved much farther away due to the expansion of space. The photons that left those distant galaxies long ago have been traveling toward us the whole time, but the space they were traveling through has been stretching, carrying those galaxies further away even as the light approached. The expansion of the universe was first systematically observed by Edwin Hubble in the 1920s. By measuring the distances to a sample of galaxies and comparing them to their recessional velocities, determined from the redshift of their light. Hubble established that galaxies were moving away from us at speeds proportional to their distances. The farther away a galaxy, the faster it was receding. This relationship, now called Hubble's law, implied that the universe was expanding uniformly in all directions, and by running the expansion backward in time, that it had originated from an extremely hot, dense state, what we now call the Big Bang. In 1998, two independent teams of astronomers studying distant supernova made a surprising discovery. The expansion of the universe is not slowing down, as most physicists had expected, given the gravitational attraction between matter. It is speeding up. The universe is undergoing accelerating expansion, driven by a mysterious energy component that has been termed dark energy. The nature of dark energy remains one of the deepest unsolved problems in physics. It appears to be a property of space itself, a kind of intrinsic energy density of the vacuum that drives the expansion of space at an accelerating rate. The consequences of this accelerating expansion are profound for the very long-term future of the universe, and for the theoretical question of how much of the universe could ever be reached. Galaxies beyond a certain distance are already receding from us faster than the speed of light, not because they are moving through space faster than light, which special relativity prohibits, but because the space between us and them is expanding at a rate that causes the distance to grow faster than light can cross it. These galaxies are beyond our cosmic event horizon. Even if we sent a signal toward them today, traveling at the speed of light, it would never reach them, because the space between us is growing faster than the signal can traverse it. Currently, the cosmic event horizon is located at a distance of about 16 billion light-years. Galaxies beyond that distance are effectively beyond reach forever, not just practically, but in principle. As the universe continues to expand and the expansion continues to accelerate, this horizon will gradually recede in terms of the galaxies it excludes. Billions of years from now, the local group of galaxies will be essentially the only visible portion of the universe, as all other galaxies recede beyond the horizon. The night sky of that future era, if anyone is around to observe it, will appear far emptier than ours. Within the observable universe, the large-scale structure of matter follows a pattern that astronomers call the cosmic web. Galaxies are not distributed randomly. They congregate along filaments and sheets with enormous voids, regions nearly devoid of galaxies between them. The filaments and sheets intersect at nodes where the densest galaxy clusters form. Seen at the larger scales, this structure resembles a three-dimensional foam or sponge, with matter concentrated along the surfaces of enormous bubbles of emptiness. The largest known structure in the observable universe is the Hercules Corona Borealis Great Wall, a massive superstructure of galaxy clusters and filaments spanning roughly 10 billion light-years. Its existence actually challenges some aspects of standard cosmological models, which predict that structures larger than about 1.2 billion light-years should not exist, because the universe has not had enough time for gravity to assemble them. The Great Wall and a handful of other very large structures remain areas of active investigation and, in some cases, ongoing debate about their reality and extent. At the very limits of our observational capability, we can see light from when the universe was only a few 100 million years old. The earliest galaxies detected by the James Webb Space Telescope are among the most distant objects ever observed, their light having traveled for over 13 billion years to reach us. Some of these early galaxies have surprised astronomers with their unexpected size and maturity, suggesting that galaxy formation in the early universe may have proceeded faster than standard models predicted. 1 light-year, measured against the 93 billion light-year diameter of the observable universe, is an almost vanishingly small unit. It is roughly 1 part in 93 billion of the observable universe's diameter, and yet it represents the fundamental barrier that stands between humanity and the stars. We cannot reach the edges of the observable universe. We can barely contemplate reaching the nearest star. The universe is inconceivably large, and we are, for now, confined to a single small world orbiting a single ordinary star, looking outward at a cosmos whose scale exceeds our ability to fully grasp. Chapter 16. Reflection, Distance. As perspective, we have traveled a long way in this video. We began with the definition of a light year, a unit of distance so large that our fastest spacecraft would take tens of thousands of years to cross it. We traced the history of measuring light speed, watched it transform from an unknown to one of the fundamental constants of the universe. We moved through the solar system, past the heliopause, and into interstellar space, and stood at the edge of the gap between our sun and its nearest neighbors. We examined the spacecraft we have built and found them beautiful and extraordinary by any human measure, and utterly inadequate to the task of interstellar travel. We looked at the physics that constrains us, the tyranny of the rocket equation, the steeply rising energy costs of approaching the speed of light, and the strange gifts that relativity offers to any traveler who could somehow get close to that limit. We explored the propulsion, concepts that engineers and physicists have seriously considered, from laser sails to nuclear pulse drives to the theoretical perfection of antimatter annihilation. We walked through the interstellar medium and felt its hazards. We contemplated the generation ship and what it would mean for a civilization to commit to a journey whose outcome would not be known for thousands of years. And then we stepped back and placed all of this within the context of the galaxy and the observable universe beyond it. 1 light year, the distance we have been examining all this time, is a unit so small at galactic scales that it barely registers. It is the space between neighboring houses in a city that stretches for 100,000 blocks. What does all of this mean? It means, first and most practically, that interstellar travel is genuinely hard. Not impossible, as far as we can tell, but hard in a way that dwarfs every engineering challenge our civilization has so far faced. The gap between what we can currently do and what interstellar travel requires is not a gap of decades. It is a gap that may take centuries to close, if it is ever closed at all. But it also means something else, something less practical and perhaps more important. The vast distances between the stars are not simply obstacles. They are a feature of the universe we inhabit, a feature that shapes what kind of place this universe is and what kind of experience it is possible to have within it. We live in a universe where information and matter can travel only so fast, where the nearest star is separated from us by a distance that our fastest probes would need tens of thousands of years to cross, where the light we see from the night sky is ancient, arriving from sources long gone or profoundly changed, where the observable universe is finite, bounded by a horizon set by the age of the cosmos and the speed of light. These facts could be experienced as limiting, and in a practical sense, they are. But they can also be experienced as part of what gives the universe its particular character, its depth, its silence, its extraordinary scale. We are creatures that evolved on a small, warm world, adapted to distances measured in kilometers and times measured in years. The cosmos we find ourselves in operates on scales that our intuitions were never designed to grasp. And yet we try. We build telescopes and point them at the sky. We launch small metal machines and watch them drift, year by year, past the planets and into the dark. We measure the distances to other stars and find that some of them harbor rocky worlds orbiting in conditions that might, under some circumstances, permit the existence of liquid water. We study the physics of relativity and discover that time itself is malleable, that a traveler moving fast enough would experience the universe differently from someone left behind. This reaching, this persistent attempt to understand a universe that exceeds our natural comprehension, is one of the more remarkable things our species does. It does not solve the engineering problem of crossing a light year. It does not bring the stars any closer. But it changes our relationship to the distance and to the darkness. The question of how long it would take us to travel 1 light year has no simple answer. With current technology, it would take tens of thousands of years. With near-future nuclear propulsion, perhaps thousands of years. With advanced fusion drives or laser-propelled light sails, perhaps decades to a century for small probes. With a theoretical maximum of antimatter propulsion, perhaps a few years. With technology we cannot yet imagine, perhaps something shorter still. But underlying all of those answers is a more fundamental truth. 1 light year is far, farther than any human being has ever traveled, farther than any machine we have built has come close to crossing, farther than any technology we currently possess could bridge within a human lifetime. It is a distance that makes honest the gap between where we are and where the stars are. And perhaps that honesty is itself valuable. To know the true scale of the challenge is not discouraging. It is clarifying. It tells us something real about the universe, that it is large, that it is old, that it does not scale to human convenience. And it tells us something real about us, that we are a small species on a small world, looking outward with instruments of our own making, trying to understand a place that is very much larger than we are. The stars will wait. They have been waiting for billions of years. And somewhere in the long future of our species, if we persist and if we learn, and if we keep building and reaching, the distance between us and them may gradually, over generations and centuries, begin to close.